Hi, welcome everyone. My name's Laurence Rouesnel, and I'm an engineering manager at Meta, where I lead part of the PyTorch team. For the past 2.5 years, I've been focusing on PyTorch libraries like Torch Vision, Torch Audio, Torch Multimodal, and Torch Rec. We do a bunch of work across generative AI, large-scale content understanding models, and large-scale recommender systems. Today, though, I'm going to be talking about the evolving landscape of data loading in PyTorch. This will be a high-level overview of the challenges we see in data loading and how the nature of these problems has changed as models get bigger and systems get faster. I'm going to start with an overview of data loading, some aspects of the problem that make it tricky to solve in a general way, and how these relate to industry trends. Finally, we're looking at building better abstractions and tools for data loading in PyTorch. So at the end, I'm going to ask anyone who wants to partner, collaborate, or help us build this together to reach out to me or another member of the team. So what is data loading? Let's start from an oversimplified model. The purpose of the data loader is to feed batches of data to your training loop. Essentially, we call next to get a set of tensors for the forward-backward pass. Throughout this talk, I'm going to use the terms data loading system and data loader interchangeably. There's a wide variety of implementations that have different designs and trade-offs. Conceptually, data loaders really do two key things. We first need to fetch some potentially raw, maybe untransformed training examples from a storage system. Then we need to pre-process the data to make it ready for our model. The data loader typically also does things like constructing a batch of the correct size and other preparation needed, like transferring the tensors to the correct device. I also want to highlight that this diagram is a conceptual model. The actual data loader in PyTorch looks a little bit different, but we'll get to that later. So let's start off by talking about fetching. Fetching data is where we access our data store. This might be a cloud object store, a file system on a locally attached SSD, a high-performance networked file system, something NFS-like or something like Lustre, a database, or maybe even a distributed queue. For each data loading system, fetching requires us to specify how to locate the right set of data and actually call the APIs to do so. For example, a user might provide a path on a file system, maybe with some filters or glob patterns. In other cases, they may use an index or metadata file to look up the right objects to load directly. For example, a CSV file with object store paths. Once we have fetched the raw bytes from the storage system, we need to transform them into tensors that are ready for the training loop. Now, the transforms are nearly always use case specific. Computer vision models, as in this example, may have to decode JPEGs, resize or crop them, apply transforms like random flips, and eventually convert them to tensors. A caveat I'll add here, since the lines can be blurry, is that generally a transform or preproc is something that we do that's not differentiable. It's not involved in back propagation. This distinction is important because we can parallelize or scale up these operations separately and independently to the model. It's this aspect that means we can spin up multiple workers and execute transforms outside the training loop. This line does get blurry though. Sometimes image, video, or audio tokenizers are also learnt models and might be trained as part of our training loop. And so in that case, they really just form part of the model. Now, the above mental model looks simple, but implementations are significantly more complex in practice, and that's the topic of this talk. So typically, each step is parallelized. We might have multiple Python processes that are fetching examples or executing transforms. Some users may choose to have dedicated services that scale out horizontally to improve performance. Most data loaders support some kind of prefetching or pipelining to execute the fetching and transforms concurrently with the training loop. You can start to see the complexity is already building up. Now we potentially have thread or process management on our hands, managing shared queues and memory buffers, and we have to deal with potential resource contention. You might also be able to tell that there's a lot of decisions here that are starting to depend on specific use case, resources available, and the type of data that you're loading. This heterogeneity is going to be a theme throughout the talk. So there are two equations to keep at the back of your mind when you're thinking about data loading. In pretty much every situation, as machine learning engineers, we want to try to improve the model QPS, or size of our models, so our training jobs complete faster and we can train larger and better models. Data loading is really only important if it becomes the bottleneck. This gives us the first formula. As long as our fetch and transform times are faster than our training step time, we don't really care about improving our data loader. One way to reduce our fetch and transform time is by parallelizing across the compute that we have available. This ties back to what we were talking before about transforms not being trainable. We can execute them in parallel and separately from the forward-backward pass. This can be on multiple processes on our training host or on maybe a separate fleet of workers. This gives us the denominator compute term. Now, the second formula makes sure that we don't slow down training overall due to resource contention. We need to be careful about the CPU and memory utilization used by data loading on training hosts. Creating more worker processes can help improve throughput, but can quickly lead to performance regressions if there's contention with the trainer. This can be particularly insidious when the contention introduces variance in training step latency. Since every trainer operates synchronously in lockstep, typically when running distributed training, the training step time is dependent on the slowest worker. If data loading causes one worker to pause because CPU usage spikes, it will cause every worker to slow down. Now, getting back to the title of the talk, how is the ML landscape evolving? And what does this mean for the data loading ecosystem? So let's look at a few examples of key trends that we've recently seen and that we expect to continue. The first trend to note is that dataset sizes are actually getting larger. We now talk about trillions of tokens, millions and billions of images. The increasing scale of datasets is actually less impactful than you might initially expect. And this is just because our system's going to get bottlenecked by model training first, as long as the equation holds true as a starting point. There are some minor impacts, since more training examples might involve more metadata to keep track of, but generally for a system that already scales, this won't make much of a difference. If, however, you're going from a training dataset that fits on a single node, whether in memory or on disk, then you may need to change something in order to go to an out-of-core regime. The actual challenge here is that typically we try to keep our training time the same when increasing dataset size. And we do this by scaling out the number of trainers or using faster hardware. So this leads us to our second trend. Training hardware is getting faster. We see this as the continuation of Moore's law. Our CPUs are getting more cores. Our GPUs compute more flops. Our systems get better. The real impact of faster training hardware is that our training step time is shrinking. This puts pressure on either increasing the amount of compute we use for data loading or improving the performance of our fetching and transforms to make up that difference. This comes out as a mixed bag, though, and because it depends on the specifics of our workload, since GPU compute, CPU compute, and memory bandwidth are not improving at the same rates. Our third trend relates to the velocity of data. Increasing the freshness of models and being able to use more recent training data is becoming more important and feasible. While this isn't true of every use case today where data acquisition relies on a lot of human input, like fine-tuning data sets for LLMs or image generation, I expect we'll continue to see pressure on how fast data is made available for training and how quickly ML engineers want to be able to use it. This impacts some of the design trade-offs that we'll talk about later. For example, packing your data for training by pre-shuffling and bundling is becoming common. And this step fundamentally slows down how recent your data can be and creates a larger cost versus cases where you have a relatively static data set. A much more significant change is that as we enter a world where multimodal models are becoming more common, the type of data models are trained on is increasing in size. The context length of LLMs is scaling up to hundreds of thousands of tokens. Images are being trained on at larger sizes, and the use of richer formats like video is becoming more commonplace. This is putting pressure on storage and processing systems as they deal with larger objects. The difference between retrieving an image versus a video is several orders of magnitude. Now, it's important to remember that as data gets more complicated, typically our models get larger and more compute intensive to take advantage. This actually means there's upward pressure on training step time as well. So overall, it comes out in a bit of a mix. Along with the size of examples increasing, though, the compute cost and shape of transforms is also changing. For example, using video today is done by sampling a handful of frames, effectively lowering the frame rate. With generative AI, though, it's important to be able to train models on higher resolution inputs and at higher frame rates that match the output to generate. The difference between sampling 10 frames at 224 pixels for a minute video versus training on 512 pixel width frames at 24 frames per second is close to 1,000 times increase in terms of memory bandwidth, storage, and compute. At the same time, we have this continued tension where our transform time is increasing, but our training step time is probably also increasing as well. So the impact is, it depends. Where there's a much larger problem for compute shape is actually with resource usage. The memory and CPU compute required for loading and transforming data may start to run into the limits of the hardware we have available on training hosts. There may also be pressure on resources as these models get more complicated. For example, decoding videos is particularly demanding in terms of CPU utilization, and we're going to use up a lot more memory buffering transform training examples. With that said, we're also seeing shifts in hardware. Over the past decade, we've seen a change in the ratio of memory bandwidth to network bandwidth to compute. As one example of this trend, cloud instances are now available with interfaces capable of 600 gigabytes per second throughput. This is orders of magnitude larger than what it was a few years ago. As constraints change, the optimal way to architect your data loading systems will also change. Moving on to what is probably the most significant change. What was once a single GPU on a single training host became multiple GPUs on a single machine, and now it's not uncommon for use cases to leverage larger clusters scaling into thousands of GPUs. This change has a big impact on data loading systems. The default paradigm today is fully synchronous training, as mentioned before. The forward-backward path of most models is fairly stable in terms of latency. Weights and gradients are shared via uncontended interconnect with low variance. Data loading, on the other hand, has higher variance. Data is pulled from storage over shared networks. Physical storage devices may have competing requests. Hotspots can develop, and transform latency may depend on the shape of the data, like the size of an image. All of these factors mean that the latency distribution of data loading is far wider than the distribution of training step time. Going back to our equation from earlier, if the max fetch time and transform latency time is strictly less than the training step time, everything's fine. We use max here because training proceeds in lockstep. One slow trainer will slow down the rest. Our average or median, or even maybe P99.9 fetch time may be less than the training step time. But ensuring our max step time is less is much harder to achieve. One slow RPC call or a timeout can result in an increase in the match fetch time, stretching into seconds. Getting throttled by your data store or getting an image that's just larger than the rest contribute to these kind of events. As we increase the number of data loaders, we're more likely to run into the long tail of the latency distribution more frequently. This will ultimately bottleneck our training performance. What was once a 1 in 1,000 event starts to impact every training step, and your training slows to a crawl. Similarly, we may also see distribution shift as we increase the number of trainers. The aggregate throughput and QPS supported by our storage systems also needs to be able to scale up accordingly. Eventually, you may need to switch data stores as you hit the upper limits of the IOPS or throughput that they support. Now, there are ways to mitigate this to hide the latency variance by using things like prefetch queues or buffers and increasing parallelism. These aren't free, though, requiring more memory and normally hand tuning. They're also potentially getting more expensive as our data gets larger and our transforms get more complicated. In my opinion, this is the largest challenge that's facing data loading systems today as a result of the ML landscape changing. Finally, independent of scaling out our training clusters, models getting larger is actually better for those of us responsible for data loading systems. As models scale out, typically the training step time increases and we have more headroom. When someone moves from training a 7 billion parameter model to a 13 billion to a 60, 70 billion parameter model, the latency increases. So this works in our favor. So we covered a lot of industry trends in machine learning and how they change the nature of data loading. The biggest drivers of this change are how training data is getting more complex with richer types of data being used and transformed, how hardware constraints are shifting and changing what's possible from an architecture point of view, and the challenges involved with latency as we scale out to hundreds or thousands of data loaders in distributed training. So where is the data loading ecosystem today? In short, it's fragmented. Most ML engineers use something built on top of the dataset and data loader APIs offered as part of the PyTorch library. You have different options depending on your use case, where your data is stored, what format it's stored in, how much and what kind of pre-processing you need to do on it. The list goes on. I'm not going to cover every option in detail. This would take hours to go through and discuss the designs, the trade-offs, make recommendations. I will touch briefly on the built-in data loader, though, briefly, since that's what most people are going to be familiar with. So this is a pretty basic starting example, which shows some of the different APIs. Users create or use a dataset, which specifies where the data is and how to get it. The data loader handles things like collating examples into batches, parallelizing fetching and transform via Python multiprocessing. It can do prefetching, and it also handles how data is ordered in terms of shuffling if you provide a map-style dataset. Now, we and a lot of PyTorch users have run into friction when using these APIs. They're hard to compose. It's hard to scale out. It's difficult to avoid Python interpreter overhead. There's no consistent way to specify filters that get pushed down to the storage system if possible. They're hard to debug when things aren't working well, and performance requires a lot of hand-tuning and knowledge of the internals. We tried to fix this with Torch Data, where we tried to build a general-purpose data loading library to address the fragmentation. It was harder than we thought. We paused our current effort in July this year. We really want to offer something better to users, but it became clear to us that the design we were working on wouldn't necessarily solve all the problems that we were seeing. Now, we're still working on this problem, and as I mentioned, we're looking for partners, excited users, and people with ideas to collaborate with. So if you have ideas or want to help out, please reach out after the talk. So with that said, I'm going to talk through the challenges of building a data loading library. If I had to sum up the complexity in a single word, it would be heterogeneity. If I had 2 words, I'd add shuffling. Now, there are a lot of reasons why it's hard. For the most part, requirements are just different across use cases, and system setups vary so much that there's no clear one-size-fits-all solution. Your design will have to make a trade-off that just doesn't work for a segment of users. The top priority and concern that we hear from users consistently is performance. We have large, expensive clusters of GPUs, and we want to maximize their utilization. We don't want our training QPS to be blocked by data loading. To achieve peak performance, users typically spend a lot of time hand-tuning their existing solutions for their most important models. So when someone compares your library with theirs, it presents a pretty high baseline to compete against. If a user isn't bottlenecked by data loading, then they're probably focused on some other problem, like improving training QPS or scaling out the model or debugging data issues. They will have to go out of their way from these higher priority things to adopt your offering. Yes, you can offer a better API. Yes, you can remove the headache of maintenance, but they'll only switch if you match or beat on performance. Now, the other thing about performance, and this goes back to shuffling, is that random access is just hard to optimize for across many systems. The more predictable sequential data access is, overall, the easier it is to build a high-performance system. So this is a good segue to talk about throughput. One key variable in our equation is the training step time. For some models, this is really short. We see this a lot for Rexus models. They're much more likely to be bottlenecked by data loading and preproc since they sustain a really high QPS with really large batch sizes. For other use cases, like training large language models, the training step time can be pretty long. We can hide a lot of compute and potential inefficiency while we're waiting for the forward-backward pass to complete. This means that what is acceptable overhead for one use case, say running everything through the Python interpreter, is a deal breaker for another where you're counting mallocs and trying to get rid of any interpreter overhead. The difference in throughput and how systems are optimized also has a large impact on the features that existing data loaders offer and users have come to expect. For example, if you're focused on high throughput for a model with low compute intensity, there's a lot of functionality you might be willing to trade off. For example, you can make multiple parallel requests and load balance fetching from data stores to avoid latency spikes that would slow down your training. However, this means giving up on deterministic ordering, which can be really useful when debugging. And we start to see this functionality being expected when you train computer vision or language models. So you will somewhat inadvertently end up building for a particular segment in the trade-offs that you make. Another huge source of complexity is the variety we see in terms of data stores. Firstly, there's just a lot of different integration points that you need to provide. While POSIX file system APIs are fairly common, there's a lot of different data stores that require bespoke integrations. Getting below the API level though, data stores have wildly different performance characteristics. Some have fast random access and relatively high throughput. An example is an HPC-style networked file system, or maybe locally attached SSDs. Others can deliver high sequential throughput when used with large files and normally have higher latency. This is pretty typical for a cloud object store. Now, this matters because it changes how an ML engineer designs their entire data loading system. If you have fast random access, things become much simpler since you can just ignore the cost of random shuffling. If you're accessing small files like JPEGs on a cloud store, then you'll need to be clever about caching and prefetching. You probably also need a highly optimized adapter to talk to the object store with lots of request-level parallelism. So the key factors that influence data loading design are how fast it is to fetch your data from your data store in terms of latency and throughput, and notably the distributions of each given your access pattern. And secondly, whether you're doing sequential or random access or something in between. Now, for high latency, high throughput systems, it's pretty common to pack your data into a bundled format, like web dataset, or even just using tarballs. If you're working with bundles, then everything becomes a lot more complicated. You need to make sure your APIs support different kinds or levels of randomness. You need to prefetch and download shards. You need to do memory management or cache eviction. There's a lot of complexity just for this use case in your API and implementation. There's also a lot of variety in terms of different access patterns. This turns up in PyTorch in the difference between map and iterable style datasets today, as well as how sampling is supported. For really high throughput systems, you might load balance with multiple parallel requests, so your ordering is just system defined. Whatever request returns the fastest is what you return. Where your data store has some constraints, you need to be a lot more careful about how you sample or access your data. For example, with bundles, you need to make sure your accesses are likely to hit a bundle that's already been loaded and cached. This results in a quasi-random orderings. If you have fast random reads because of the data store, you can afford map-style APIs and do efficient random reads. You can even customize your sampling strategy a lot, doing things like weighted sampling by class. API design for all of these different access patterns is pretty hard. It becomes easy for users to shoot themselves in the foot if the abstractions aren't clear. We've run into issues where users have started shuffling only within a bundle or shard. They create large in-memory buffers, which then cause out-of-memory errors or are unexpectedly slow. So this is an area where getting the design right is tricky and somewhat workload, data store, and file format dependent. The final two areas go hand in hand, but are distinct. When you use PyTorch's native dataset and data loader, the compute topology looks like this diagram. For each trainer on a host, so typically one trainer per GPU, we start multiple separate processes which actually go fetch the data and transform it. This is a reasonable starting point, though it starts to break down if we start to cause resource contention on the host. This can happen for a lot of reasons, and this relates to how different each training environment is set up from a hardware perspective, as well as the transforms we're actually running. A user might max out their CPUs decoding videos. In that case, it might make sense to offload fetching and transforms to a different set of hosts they can scale independently, as long as they have the network bandwidth. Another won't have a problem because the ratio of CPUs to GPUs on the cluster they have access to is different. The same tensions apply for the amount of memory capacity, the network bandwidth, these other resources that are available. So in many cases, it makes sense to separate out where our data fetching, transforms, and training loop run, and scale them independently. This is one example topology, but you can imagine others. For example, we might keep transforms in our training host, but scale out our data fetches. So the optimal compute topology, where to run your fetching and transforms, depends a lot on the cost of fetching and transforms in terms of the CPU compute cost and memory required and required ingress and egress network bandwidth. It can depend on your model. If your model's CPU bound, then you may run into this contention really easily. And it also depends on the hardware that's available, and this changes from user to user. So designing a system that just works and offers high performance and doesn't run into any bottlenecks is just really hard. There's just a lot of complexity and variance to abstract over. So in a word, heterogeneity. So what did we learn? Data loading is a complex space with significant heterogeneity. New challenges are being created by industry trends, like how we've gone from single machine to multi-machine to large cluster training, and how the types of data, like videos, and how they're being used are driving up compute requirements. I'm going to finish up with a closing thought. This problem's hard. Building a general purpose set of APIs and abstractions requires navigating a lot of tricky problems. We're actively working in this area. We'd love to partner with people interested in this space. So if you're dealing with some of the problems we discussed, or if you have solutions to them, or even just ideas, please reach out and let's talk after this session. Thanks everyone for listening.